It's faded a little with deep learning, but hopefully either this will inspire people to start looking into it, but also I think some of the ways that we think about things in Bayesian non-parametrics can also give you new ways of thinking about other fields, thinking about how we manage dimension in deep learning, for example, or other areas. So even if you don't, I hope you do, start working on Bayesian non-parametrics after this, then hopefully it will still help you in related areas to think differently about problems.
Yes.
And I'm actually going to spend the first hour not talking about Bayesian non-parametrics. So sorry for the false advertising. I know we've had a lot of Bayesian non-parametric, sorry, not a lot of Bayesian work today. I know you all were listening to Tamara Broderick earlier today, and there's been several Bayesian people. But I'm going to be talking maybe from a more statistical viewpoint in some of this, so really drilling down into some properties of distributions. And I know while some of you probably have Bayesian or statistics backgrounds coming in, not everyone's going to. So I'm first going to start talking about why we do Bayesian inference and how we do Bayesian inference in a parametric setting before getting into the non-parametric. So without further ado, let's start with that introduction. So let's start with a really fundamental question here of what does it mean to be Bayesian? Now, this is a question that I ask at the beginning of all of my Bayesian talks, and I get a variety of answers. I'm not sure whether I can see the chat while I'm looking at this screen.
Someone says, I have a belief.
Oh, perfect. I've now figured out the technology of being able to see your chat, so that's great. So yeah, we've got have a belief, being able to excellent. So being able to estimate uncertainty. I can tell that we've had some Bayesian talks so far, so this is great. No one's going for the gotcha, which is what I normally hear first, which is uses Bayes' law, which is true. Bayesians do use Bayes' law, but non-Bayesians also use Bayes' law. Right? That's a standard tool of both Bayesian and frequentist statistics. And expressing uncertainty is also really important. That's one of the comments that we've got. But again, that's something that frequentists do as well. Right? Anyone working with probabilities wants to work with uncertainty in some form. So confidence intervals, which is a standard frequentist tool, also expresses uncertainty. And then we've got a lot of questions which lead on to what I'm about to say, which is actually to figure out what it means to be Bayesian, we need to ask a more basic question. What do we mean by probability? And we probably all have an idea of what is meant when I say I have a coin and it's going to return heads with probability 0.4. Okay, that's kind of the first idea of probability we're introduced to. We know that that means that if we toss the coin repeatedly, the proportion of heads is going to tend to 0.4. Right? We know that if we toss it 10 times, we won't necessarily get 4 heads. But if we toss it 10,000 times, we're going to get approximately 4,000 heads, and so on. That proportion is going to tend to 0.4. And this is the frequentist interpretation of probability here. The probability directly corresponds to a frequency with which something would happen if we were to repeat it infinitely many times. So it's directly tying the idea of probability with the idea of proportion. Okay. And that's like very clear, very intuitive, but it kind of falls apart when we have a statement such as the probability of alien life existing in this galaxy is 0.4. Now that makes sense to us as a statement that someone could say, but it doesn't make sense to think about it in that classical frequentist way of discussing probabilities. There's only one of this galaxy. We can't rerun the simulation of the universe again and again and again and count how many times there are and aren't aliens. What this statement is, and what several of you have said in the chat, is a statement of degree of belief or degree of certainty. Okay, this is a measure of how the extent to which I believe there is alien life in this galaxy. Now, this may seem a little more wishy-washy, right? Because it's a subjective probability. My belief is going to be different from your belief, is going to be different from a cosmologist's belief. But we can still apply all the rules of probability to this definition of belief. Right? And that's what we're going to do. And everything after that in Bayesian versus frequentist statistics follows on from this key difference. If you are interpreting a probability as a proportion or a frequency, that leads to certain things that you're going to do that make sense to do. If you're interpreting probability as a measure of belief, that leads to other things that you will do. Okay, so we have two views of probability, the frequentist and the Bayesian. Now, a random variable loosely is a variable we can describe using a probability distribution. So if I have a coin and I tell you I'm about to flip that coin, what I get is going to be a random variable. And that's true whether I'm a Bayesian or a frequentist. So from a frequentist point of view, I could flip it, well, I couldn't flip it infinitely many times, but I could imagine flipping it infinitely many times and getting a proportion of heads. If I'm a Bayesian, I don't know what it's going to be, but I maybe have some belief based on my prior experience of coins. But moving on to something slightly more complicated, not much more complicated, we'll get more complicated. Let's say I have a coin and it has some unknown bias. And I toss it 3 times, and I'm going to tell you I got heads, heads, tails. I have 2 variables, the bias P and the sequence X. What I want to know is, oh yes, thank you. I think Rodrigo has just pointed out that there's about to be a quiz on Slido. And there is about to be a quiz on Slido, if you can put that up there. Which of these are random? And which of these are fixed? So I'm not sure, Rodrigo, I assume you can see when some sufficient number of people have voted on this?
Yes, I am looking at it. So people are voting, and let's wait a bit to share the results.
Sure. Oh, okay. Now, I think I was the first to vote. So, and now it's letting me see it. You're all learning Bayesian non-parametrics, and I'm learning Slido. Okay, so we seem to have the numbers jumping around a little. Currently, we've got a slight majority saying X is random, P is fixed, but it's really all answers have a significant amount of support here. I'm sorry, I didn't realize that me going to, again, I'm learning Slido. I didn't realize that me going to Slido would interrupt my screen, so apologies about that. So that was kind of a trick question in that all of the answers, it depends what you mean by a probability. So the answer to that question depends whether you're thinking like a frequentist or thinking like a Bayesian. And neither of those are right, so all of the answers are right. So remember, the frequentist viewpoint is that something that is random is something that will change according to some probability distribution if we repeat it. By contrast, something that's fixed is something that isn't associated with a probability, which means it's not going to change if we repeated the experiment. Whereas from a Bayesian viewpoint, something that's random is something that's uncertain. And something that's fixed or not random must therefore be something that we're certain about. Now, in this case, our sequence of heads, we know what it is. We know we got heads, heads, tails. But it would be different if we repeated the experiment. And our bias is unknown, right? We don't know the bias, but we know it's a constant. We know it would be the same if we repeated the experiment. We still wouldn't know it if we repeated the experiment, but it wouldn't have changed. The coin, that's a property of the coin. So it follows that if I'm thinking like a frequentist, that something that is random is something that would be different if I repeated it. The sequence of coin tosses is random, but the bias is fixed. But from the Bayesian viewpoint, I'm not uncertain what I saw. Right? I know I saw heads, heads, tails. So that's fixed. I don't know what the bias is, so I have uncertainty about what the bias is. So that is random. And that basically is what leads to Bayesian inference, this idea that we have uncertain parameters or uncertain components of our models, and that because we use probabilities to express uncertainty, we can put a distribution over those, and we can update that distribution as we see more evidence to support different values. So this kind of leads to the general recipe for Bayesian inference. And this is going to be what you see pretty much anytime you see Bayesian inference. Sometimes it will be complicated and obscured. Sometimes it will be really obvious, but this is what's always going on under the hood. We're going to come up with some class of models that we feel is rich enough to express the variation in the world, and we're going to parameterize that by some set of parameters. We don't know what those parameters are because we're not all knowing. So we're going to put a prior distribution of those parameters that captures our initial beliefs. We might not really have any initial beliefs, in which case we'll put something very vague and uncertain. Or we might have a lot of insider knowledge. We might have experience with the problem, in which case we can express that prior belief in these priors. We're then going to see observations, and we're going to use Bayes' law to update our posterior distribution. Right? So our posterior distribution over the parameters is going to be proportional to our prior distribution times how likely it was we saw what we saw. So as a concrete example, let's imagine I am trying to model heights in some population of a country I've never been to. And so I might think, what's a good distribution for heights? Well, most things tend to be bell curved, so I'm going to use a Gaussian. And then I'm going to think a little more and think, well, men tend to be taller than women, so I'm going to use a mixture of two Gaussians. So I have a model, mixture of two Gaussians, where I don't know the proportion, and I don't know the means and variances of those Gaussians. So I'm going to put a prior distribution on those. So maybe I know that most countries have roughly equal men and women, so my prior on the proportions would capture that. And I know that most people are between, say, 5'5" and 6'2". So maybe I'll put a prior that sort of centers its probability on that for the means. I'll then start measuring people's heights, which might be a little rude when you first visit a new country, but in this example, we're going to do that. And then I'm going to use Bayes' law to update my posterior distribution over what those proportions are and what those means and variances are. But the challenge here, and the key to making this work nicely, is picking a good prior. Right? So in that case, I went with something that seemed reasonable, but maybe it's not flexible enough. Right? If my model isn't flexible enough to capture something close to the truth, I'm never going to get that truth. So in this example, I assumed that there were going to be two clusters that I hypothesized were for men and women, but maybe that's not enough. So maybe I know that we have, for example, different average heights for different races. So maybe I should have more than two clusters. And this is something we see in a lot of modeling problems. We know we want to do some sort of clustering or dimensionality reduction. We just don't know what the appropriate dimension is. So if I wanted to do a topic model of the New York Times, I don't know what the right number of topics in the New York Times is. And if I'm learning that topic model on a fairly small training set, I might not have captured I might not have seen all the topics before, right? If I trained on the New York Times from 2019, I probably would not have topics for COVID-19 and pandemic and all of the things that have happened since then. So Bayesian non-parametrics is going to give us a framework for having flexible priors, and in particular, it's going to be flexible in terms of this latent dimensionality. So what do we mean by non-parametric? The first time I heard non-parametric Bayes, I feel fairly reasonably assumed that was Bayesian inference without any parameters. And that's not quite true. It's kind of a misleading name. So let's first think what we mean when we say a parametric model. Well, yes, it's a model that has parameters, but in a Bayesian context, specifically, it's a model with a fixed, pre-specified set of parameters. So that mixture of two Gaussians that we discussed, that's a parametric model with 5 parameters, 2 means, 2 variances, and 1 probability vector, which decides the proportions of the 2 clusters. If we're doing linear regression in a Bayesian context, that's also a parametric model. We have a fixed dimensional vector beta, which is going to give us our intercepts and our slopes. And we have a variance sigma squared, which is going to tell us what the residual variance is going to be. A non-parametric model is one where we have we don't have a fixed pre-specified number of parameters, but instead the number of parameters can grow with the data set size. Right? So we still have parameters, we just have an unbounded number of them. And we do this by saying, okay, we're going to assume a priori that we have infinitely many parameters. So instead of having 2 components in our mixture model, we're going to assume we have infinitely many components. Instead of having a finite dimensional parameter vector beta, we're going to have an infinite dimensional parameter vector beta. Now, this sounds like it introduces more problems than it solves, because infinity is really big. But we're going to see that actually this gives us something that we can work with in a reasonable manner. So before we get into how we work with these infinite dimensional objects, I want to drill down a little into how we work with parametric models. I'm going to focus today on that mixture modeling case because that has a lot of the properties that we're going to be interested in. So here's a data set, and I want to model it using a Bayesian model. Now, in this case, the dimensionality is pretty clear. Right? There seem to be 3 clearly defined components, and they look fairly Gaussian. Spoiler, that's because I generated it from a mixture of 3 Gaussians. So I don't need to worry too much about the number of components. I'm going to just use a mixture of 3 Gaussians. So I have 7 parameters there, 3 means, 3 covariances, and a probability vector that gives the probability of belonging to each component. And so explicitly, I've assumed that given these parameters, the data was generated by repeatedly sampling one of the 3 clusters according to that probability, and then looking at the mean and covariance for that cluster, and then sampling a data point from a multivariate normal with that mean and covariance. Now, to finish off my model, I also need to put priors over those means, covariances, and over that probability vector. Okay. And we'll hold off for now on what those priors are and start looking into that in a couple of slides. Now, once we set this up, then we can start doing fun things, right? So I've specified my prior. Here I've assumed that the prior on each of the clusters is the same. So the overall prior is the probability of the proportions times the probability of each component's parameters. I know the likelihood of my data, right? I know that I'm assuming the data was generated according to a mixture model that I just specified. I can integrate out these prior distributions to get the overall marginal probability of my data. And then if I want to update my beliefs about the parameters, I can use Bayes' law to get my posterior distribution, the probability of those parameters, conditioned on what I've seen. And so here I'm just using Bayes' law. Probability of A given B is probability of B given A times probability of A divided by probability of B. So that's all great. And this equation is most of Bayesian inference. The trick comes in that integrating is hard. And sometimes it can be like beyond hard and intractable. So in order to calculate this posterior in general, we need to be able to do this integral to get the marginal. And yeah, integrating sucks and sometimes is not tractable. But sometimes we can make this easier by choosing particular choices of priors. So let's consider that prior distribution over the proportions pi. We're going to use a distribution known as the Dirichlet distribution. So hopefully some of you have come across the Dirichlet distribution, but probably there are some people who this is new to, and probably there's an in-between stage of people who've come across it but haven't really thought about what it means. So for those in the first class who haven't come across the Dirichlet distribution, this is your lucky day. It's a great distribution. It's a distribution technically over the k-1 dimensional simplex, which is just a fancy way of saying probability vectors of length k. Right? K-1 dimensional simplex, because once you know the first k-1 elements of a probability vector, you know the final element. And it basically is the same as the beta distribution, which you probably know is a distribution over probabilities, but it extends this to a multivariate case where instead of having a distribution over a binary probability, you have a distribution over a multivariate probability. And it's parameterized by a vector of positive numbers. And if we take this vector of positive numbers, alpha, and we normalize it, that gives the expectation of the Dirichlet. Right, so here on the left, I have a representation. So each of these triangles is a representation of a 3-dimensional probability vector. Right? So the corners correspond to 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the very center corresponds to a third, a third, a third. And if we have alpha equals 1, 1, 1, then that's actually just the uniform distribution on the 2 simplex, on the space of all 3-dimensional probability vectors. And that extends. If I had Dirichlet 1, 1, 1, 1, that would be uniform on the 3 simplex, and so on. So in this case, my expected sample is going to be the probability vector a third, a third, a third, but all probability vectors are equally likely. Now on the right, I have alpha is 5, 1, 1, right? So I have, if I normalize that, I can see that I'm expected to get something that has highest probability on the first component. And that's what we see here on the right. This is the PDF over the simplex, and it's concentrated on that first corner. Then in the middle, we have something that's concentrated somewhere between the second corner and the third corner. Right? So alpha, if we normalize it, gives us our best guess for what that probability distribution is. So if I'm not sure, I'll probably just go 1, 1, 1. Now, the relative values tell us the expectation. The size of the alphas tell us how much variance we're going to get between samples. So it's kind of like an inverse variance, this total sum of the alphas. The larger this sum is, the less difference is going to be between repeat samples. So here I've got, again, 3 Dirichlet distributions. They all have expectation, a third, a third, a third, because
Seems we're having a problem with connection of SINEAD, so No problem.
Hopefully it's going to stay. I have no idea where I was when when I cut out. Let me go back to screen sharing. Okay, have we been on this?
Yes, we have seen.
Okay, so I'd started talking about the inverse variance. Okay, so recap. We had the Dirichlet distribution. It has the parameter alpha. Normalizing that gives us our expected value. And then if we increase the magnitude of the alpha, we're going to tend to get less variation between the samples. So in this case, they're all going to be closer to a third, a third, a third. And if we decrease it, we're going to get more variation. So we're more likely to get things like 0.9, 0.05, 0.05. So the Dirichlet distribution has a number of nice properties that are going to make it really convenient to work with. So this is what the PDF of the Dirichlet looks like. Right? We have some normalizing constant that depends on the alphas, and then we've got a product of terms involving the actual probabilities. And we're going to use this, remember, in a clustering model. So we're assuming that our cluster indicators were generated by sampling IID from the pi that we got out of this. So the overall likelihood conditioned on pi is going to be the product over all the pi's of that entry of pi to the number of times we've seen that component. So here, m sub k is just going to be the number of times we've picked component k. Now, we want to look at the posterior distribution. Posterior is going to be proportional to our prior times our likelihood. Right? So I'm going to drop the normalizing constant in the Dirichlet and just directly multiply the Dirichlet prior and that multinomial likelihood. And we get something that looks pretty similar to what we started with. Right? So this posterior seems to be proportional to our original form, except instead of having alpha k minus 1, we've got alpha k plus the number of times we've seen component k minus 1. So this means that it must be a Dirichlet distribution. Right? It's proportional to a Dirichlet distribution with updated parameters. And we know that the only distribution proportional to a Dirichlet distribution is a Dirichlet distribution, because all distributions have to integrate to 1. So we know that our posterior is, again, a Dirichlet distribution with updated parameters. And this is convenient because we've managed to sidestep doing that integral in Bayes' law. So now we can easily do inference, update our distributions without having to integrate anything. And this is something that you may have come across before. It's known as conjugacy. It's a class of priors where if we combine that prior with an appropriate likelihood model, we can get the posterior by just combining the parameters of the prior and the observations without having to do any integration. And with this, we can then do inference fairly easily. So let's say I know the cluster assignments of each data point, and I want to figure out the distribution over pi. Well, I know that's a Dirichlet distribution conditioned on these cluster allocations, and I can sample from that distribution. Then, once I've sampled the value of pi, if I fix the values of the means and covariances, then I can sample from the posterior distribution over the cluster allocations, right? That's going to be proportional to the prior probability of it belonging to a certain cluster which is the pi k, times the likelihood, which is our normal. And then I can pick conjugate priors again on the mean and the inverse, and the covariance. And that will allow us to do something similar to update the mean and covariance parameters for each cluster. And then we can cycle through sampling the pi's, sampling the means and covariances, sampling the cluster allocations, and that will eventually converge to give us samples from the posterior. So if you're familiar with Bayesian inference, this is what's known as a Gibbs sampler. I'm not going to focus a huge amount on inference today, but this is a property that allows us to work with this in a nice manner. Now, we've come up with a distribution over pi, but rather than explicitly instantiating it like we did here, we can also integrate that out. Now, conditioned on pi, we assumed that the observations, the cluster indicators were independent, right? They were all IID samples from pi. If we integrate out pi, they're no longer independent, right? And we can do that math, and we end up with this form for the conditional distribution of the cluster indicator for the ith data point conditioned on all the previous. Now, rather than think too much about this integration, we're going to represent this in terms of an urn analogy. So if you get any further into Bayesian non-parametrics, you'll find out that we love urn analogies. So imagine I have an urn. Now, I'm not very good at drawing, so my urn is a square. And I am going to put in that urn k different colored balls. So here I've got orange, gray, and blue. And each of those balls are going to be size of the corresponding alpha parameter. So here I've picked them all to be the same size. I'm then going to reach into that urn, and I'm going to pick out a ball with probability proportional to its size. So here I've picked a gray ball out. I'm going to return that ball to my urn, and I'm also going to return a new ball of size 1, which is the same color. Then I'm going to do the same again. So here I've reached in, I've picked a blue ball proportional to its color, proportional to its size. I'm going to return that plus a new size 1 blue ball. And then maybe next time I pick one of the new balls, I reintroduce it plus another blue ball. And in this manner, I can build up a data set. Okay, so let's now move on to the second poll in the Slido.
It's already live. So
it's already live. Excellent. Okay, so let's say we're starting with just 2 balls in there, both of size alpha. And I'm going to sample 20 samples from that scheme. Okay. If I increase alpha, what's going to happen? Am I going to get more balance between blue and red, less balance between blue and red, or is it going to be basically the same? I'll return to my picture of my urn so you can see that. Now, because I've returned to the picture, I can't see my Slido. So Rodrigo, I will let you tell me when we've got some answers.
Yes, I will.
So as you're thinking about it, you might find it helpful to go back to the very first draw where we picked out that one gray ball and think about if you started from here but increased or decreased the size of the original balls, how is that going to affect how many gray balls you expect to see?
So the first option was that alpha will not affect the value.
Okay, so okay, let me put an answer in. Okay, so looks like we've got 3 answers so far. Sneaking peeks. So let's maybe wait a moment and see. Oh, have we gone on to the second question?
Yes, actually. So we
I'm sorry. I thought we were still on the first. Okay. The polls both look very similar, so I got lost. Okay, so let's maybe talk about that first question then. Mea culpa. So I was asking if we have 2 balls, red and blue, how is the final proportion of red and blue going to change as we increase the alpha? So let's first imagine we had those 2 initial red balls were size 0.001, right? Tiny, tiny red and blue balls. We're going to pick one of them, and let's say it's blue. We're then putting in a size 1 blue ball along with those 2 tiny red and blue balls. Once that happens, we're going to pick the blue one again, right? Because we've got a mass of 1.01 blue and 0.01 of red. So we're going to keep getting that blue. Occasionally we'll get the red, but we're going to keep getting that blue because the mass of that first ball that we put in overwhelms the mass of the original starter balls. On the other hand, if we had 2 initial balls of size 100, first maybe we pick out a red. We'll put that back in and we'll put a ball of size 1 back in. We're still roughly just as likely to pick red or blue. Right? So the larger alpha is, the larger these original balls are, the more similarity there's going to be between the different components. Right? Whereas as it gets smaller, the weight of those original balls is going to get drowned out by the signal of what we see. So we're going to end up with either a huge number of red and very few blue, or a huge number of blue and very few red, depending on which one we started with. So the question that we then moved on to, which I didn't realize we'd moved on to, was, okay, let's imagine we have a larger number of initial balls. Let's say we have 20 initial balls. And we're going to do the same thing. We're going to repeatedly sample. Now imagine you have those initial balls being size 0.01, 01, 01, 01, 01, 01. You're going to pick one of them. And then let's say we pick the first. You put that 0.01 ball back. You put that size 1 new ball in. And now suddenly you're way more likely to pick that first one again, right? So we're going to see that first ball disproportionately more often because it's starting to overwhelm the probabilities. That means if we only pick out 20 times, we're not going to get that many different values because it's going to keep tending to pick that first one because we've added more balls in. By contrast, if we started off with 20 size 100 balls, maybe again, we first pick the first one, we put it back, and we put in a unit-sized ball. We're still fairly likely to pick a different option, because while the first color has mass 101, the second color has mass 100, the third color has mass 100. So as those alphas increase, we're going to tend to get more clusters come out in a finite number of samples. So is there any questions on that? That's kind of like looking at your survey responses, that maybe isn't what your intuition said, which is good. Probability sometimes is a little unintuitive. But does that make sense as to why changing the ball's original size will change what's likely to happen next? And I'll note that this is exactly the same thing as we saw on those pictures of the simplex. As the alphas increased, we were more likely to get our probability be a third, a third, a third. As they decreased, we were more likely to have them closer to 1, 0, 0 or 0, 1, 0, and be more concentrated on one of the clusters. Okay, so more questions, yet more chances for me to get Slido right. Okay, so, and I think for this one actually, oh sure, let's do the poll. So in my example, I happened to first pick out a gray ball. Okay, that was my first thing that I sampled. Does the fact that the first ball was gray change the probability of subsequent balls being gray? Does it change the expected number of gray balls I get after that? Okay, so do we have that? Oh, I've been logged out of the event. Okay, so looking at the numbers so far, the consensus seems to be, let's see, a few more to come in. But the majority seem to be saying that yes, the probability of the ith ball being gray does indeed depend on how many of the previous balls were gray. And yes, that's true, right? As we're going into our urn, if we've already seen 10 gray and 0 black or blue, sorry, I forgot what color was there, we're more likely to hit a gray than if we'd seen 0 gray and 10 blue. Okay, we have more gray balls in there, so we're more likely to pull out a gray ball again because there is more total mass of grayness in our urn. So this means that in this urn representation, where we've integrated out pi, our observations aren't IID, right? The cluster allocation of the ith component does depend on the cluster allocations of everything we've seen before. Right? And this is because we've integrated out the underlying probability vector. Now we have this conditional dependence. So that then raises a slightly more subtle question. does changing the order of my sequence matter? So am I equally likely to pick 3 gray balls, then 1 blue ball, and then 1 orange ball, as 1 orange ball, 1 gray ball, 1 blue ball, 1 gray ball, 1 gray ball? Or are those going to have different probabilities? So this is a little more of a subtle question. And you might want to think about sort of sketching out what the probability of the different outcomes is going to look like mathematically. Okay, so we're still going through that. Let's give it a few more minutes because they're currently, yes and no, are pretty close. So maybe you can be the deciding factor in which one wins. And I say, I like that no one is going for don't know. I like that everyone's being bold in their choices. Although it's totally fine to say that you don't know. But I like everyone's confidence. That's really important. Okay, so as I'm looking at it now, I'm seeing that the majority have gone for yes. The probabilities are the same. So let's take a look. Let's try, okay, so the way I've written this, no, this was bad slide writing of mine. Yes, they are the same. No, the order doesn't matter. So the majority of you are right. So let's look at why. The first time we picked out a gray ball, that had probability of the size of the original gray ball over the sum of the sizes of the original balls. Next, if we pick out another gray ball, we now have 1 size alpha gray ball and 1 size 1 ball in there. So the probability of picking another gray is going to be proportional to that total gray mass over all of the total weight of the balls in there. Then we're going to pick another gray. That happens with probability proportional to that initial gray ball plus the 2 unit balls that we've got in, because we've just had 2 grays, divided by the total mass. Then if we pick a blue one, that's probability proportional to that original blue ball, again, divided by the total mass, and so on. And I can write that down for any other sequence. And I've totally messed up the numbers on that sequence, which I didn't notice when I was doing my run through. But the probability of the first one will be the size of a green ball divided by the total mass of the other balls times the size of the red ball divided by the total mass of the other balls, and so on. So in each case, we are going to end up with the same numerators and the same denominators, just in different orders. So you'll see that the denominators are the same because that's just the mass after adding 0, 1, 2, 3 balls. We're going to pick a gray ball 3 times. So that means we're going to have 1 time where the probability of picking it is proportional to that initial gray ball, 1 time where it's proportional to that initial gray ball plus 1, 1 time where it's proportional to that initial gray ball plus 2. So the overall probability doesn't change, and this is a property that you'll come across a lot in Bayesian inference called exchangeability. So we're in this situation where, yes, the probability of the ith ball being a certain color does depend on the previous balls, but if we take the probability of the whole sequence and shuffle that order, the probability doesn't change. Now, this is a property that makes it really handy to work with this Dirichlet distribution, because it means that we know that we can always treat a ball as if it was the last one we saw, right? When we're considering the probability of a data point belonging to a cluster, we can pretend it was the last one we saw and conditioned on the all of the other data points. So we can rearrange our data points so that we're always looking at the last one. And this is going to be a really convenient property when doing inference. It makes it very easy to, rather than deal with the entire data set at once, break it down into individual subproblems, so we're only looking at the conditional distribution of one cluster given everything else. So we spent a long time on the Dirichlet distribution. I'm going to cover very quickly 2 more properties, and then I'm going to suggest we take a quick break, go and get a glass of water, shake your legs before we return to some non-parametrics. But first, I'm going to introduce 2 important properties that we're going to make use of after that break. The first is what's called the agglomeration property. And this says if we have a k-dimensional Dirichlet, we can squish elements together to get a smaller probability vector. And that smaller probability vector is still going to be a Dirichlet random variable. So let's say I have a k-dimensional probability vector that I've sampled from a Dirichlet with parameters alpha 1 through alpha k. I can take the first 2 elements and sum those together, right? That gives me a k-1 length vector. If I do that, then that vector is going to be also Dirichlet distributed with parameters where the first parameter is the sum of those first 2 original parameters, and all the other parameters are the same. So if you're stuck with nothing to do tonight, this is actually fairly easy to prove from that definition of the Dirichlet that we saw earlier. But I'm not going to go into the proof because we got enough math for today. And then the second property is going to be the opposite. Right? So the agglomeration said we can take a k-dimensional probability vector and squish elements together and still have a Dirichlet distribution. It makes sense that we can do the opposite. We can take a short probability vector and separate the components out so as we have something longer. Now this is a little trickier because there's only one way you can add 2 numbers together. But once you've got that number, there are infinitely many ways you can split it in 2. So the way this is going to work is, let's say I have a k-dimensional probability vector and I want to split the first element in 2. And I'm going to sample a beta random variable whose parameters are going to be the parameter of that first element times some number b between 0 and 1. And then the second one is going to be the parameter of that first element times 1 minus that b. I'm then going to use that proportion to split the first element. And that then is going to give me a expanded Dirichlet distribution where the parameters are that first element times that b, that first element times 1 minus b, and then the remaining elements. Okay, so that's been an awful lot of information about the Dirichlet distribution. But that's going to give us the framework that we need to move on in a few minutes to the infinite dimensional and the analog of the Dirichlet distribution, which is the Dirichlet process. So I'm going to take a pause for, let's say, 3 minutes. So I'll be back here at 8 minutes past the hour, wherever you may be. I'll stay here in the meantime in case anyone has any quick questions on what we've covered so far. find how to turn my video back on. Just saw a question in the chat saying, what is the meaning of theta in this case? So theta here, so what I wanted to do was take my k-dimensional probability vector and take one element and split it. So there's infinitely many ways I can split that element, right? I can split it anywhere between 0 and 1%, 0 and 100%. I can split it 50-50. I can split it like 30-70. So theta is just that amount that I'm splitting it, right? So at the bottom, in my original Dirichlet, the first parameter had size pi1, and I'm going to split that into two, where the first one is going to be pi1 times theta. And the 1 should not have been there. I guess I got carried away with subscripts. So pi1 times theta. The second one is going to be pi1 times 1 minus theta, right? So that the total mass of those two is still theta. Is still, sorry, pi1, so it's still a probability vector. But we're making this break be random, and it's random in a way that depends on both that original parameter and some number that I've chosen. And we need this additional step of having the theta in the splitting, but not in the pulling together, because whatever theta is in this case, if we do the agglomeration and push it together, we'll still have one element that's size pi1. But we need to decide exactly how to split it apart again if we're doing the opposite. Okay, so according to my phone, we're at 3 minutes. So let's move on to some actual non-parametrics. So the Dirichlet distribution is a great distribution, right? It has a lot of ways of thinking about it we've looked at. It has nice properties such as conjugacy, but it has got this fixed choice of k. Right? So we have, in everything we've seen so far, explicitly assumed we know how many clusters we want, and then we picked a Dirichlet distribution of that size. And that was fine in our previous example where there were clearly 3 clusters. But sometimes it's hard to tell. So sometimes we get data that looks kind of like this. And it's hard to know what the right number of clusters is. So maybe I think there's 3 clusters here, right? So I've colored those in green, red, green, black, and red. But maybe I think there's more than that. Maybe I think these outliers over here are a different cluster in blue. Or maybe there's actually 7 clusters, right? And there's this long yellow cluster over here, and this pink and cyan cluster here, right? It's hard in these cases where you have a lot of overlapping clusters, some of which are smaller than others, to know how many components to use. And this is going to be particularly true in cases that aren't 2-dimensional Gaussian data, where you can't just eyeball it and guess. And even if I have gotten a good guess of how many clusters there are in this data set, that might not be all the clusters that exist in the entire population. Right? So here I have a couple of 100 data points, and maybe 7 data points is the right number of clusters for that. But maybe if I gathered another 1,000 data points, I would start seeing more clusters that weren't in my initial training set. So a good rule of thumb to deal with both of these, the how many clusters are there and have I seen all my clusters, is to make sure that we're going to have more clusters than we actually need. So far, we've been working with finite dimensional mixture models where we have k components. But we want to make sure that we never run out of components. So we're going to make sure k is really big. And when I say really big, we're going to make sure k is infinitely big. We're going to make sure that no matter how many data points we have, we can never run out of clusters. And we can write this down, right? We can write down this likelihood. Instead of being a mixture of k, we've now got infinitely many components. So infinitely many probabilities and infinitely many means and covariances. And this sounds like it would be a terrible idea because we don't have infinitely many computational resources. It is impossible for us to represent infinitely many means and covariances. So this seems like it would be a non-starter to begin with. However, we're working with a clustering model. And in this case, every data point can only belong to at most one cluster. So we know that even though we have an infinitely large mixture model, in practice, we're only going to see at most n clusters. And also, it would be a really bad mixture model if we always had the same number of clusters as we had data points. Right? That's not really a clustering model. In practice, we're going to have fewer clusters, almost always, than we have data points. This is going to arise naturally if we have some of our probabilities, some of our pi's being bigger than others. Right? If you have one pi that is size 0.5 and all of the rest are vanishingly small, we're going to see that size 0.5 cluster more often than we see the other clusters. So having this infinite dimensional mixture model means that no matter how much data we see, we can always add more clusters. There's always more room. But we're still, in practice, going to only be seeing a finite number of clusters. At most, the number of data points, but in practice, it's going to be some random number lower than that value. Okay, so something here said KDE uses n Gaussians. And that does work fine. And yes, I'm not saying so. And that also, so KDE actually is an example of a non-parametric model, right? We have an increasing number of components as we grow. Here, though, I am explicitly wanting to do a clustering model, right? I am wanting to draw similarity. I'm wanting to have a model that is more like a finite mixture model where I am learning some structure. So yes, a KDE does work absolutely fine for density estimation, but it doesn't tell us these two data points belong to the same cluster and these two do. So yes, that's a very good question. We don't need the clustering if we're not interested in making use of it. Okay, so let's assume we do want a clustering model that has these properties. We're going to want something that is like a Dirichlet prior, but has an infinite number of components. And we're going to sneak up on this using that decimation property that we introduced using the break, where we started with a k-dimensional Dirichlet, and then just kept splitting the components. And I'm going to start off with the smallest one we can get, which is 2-dimensional. And I'm going to specifically say this is a Dirichlet alpha over 2 for some alpha. So that's actually a beta, alpha over 2, because remember the Dirichlet is the multivariate beta. And so then I have got a 2-dimensional probability vector. Here they're about 0.68 and 0.32. I'm then going to recurse on each of these. And I'm going to split them using that beta splitting rule. Right, so I'm going to take the first one, I'm going to sample theta 1, which is a beta random variable, where the parameters are the original parameter for that first one, which is alpha over 2 times b, and alpha over 2 times 1 minus b. And I'm just going to take b be a half for all of this to make it easier. If I do this, I now have a 4-dimensional Dirichlet distribution whose parameters are alpha over 4, alpha over 4, alpha over 4, etc. And I can do that again. So now I'm going to split each of those 4 components to get a Dirichlet alpha over 8, alpha over 8, alpha over 8, etc. And I'm just going to keep splitting, right? 32, 64, 128. And you can kind of imagine doing this and sort of squinting as it gets fuzzy and we get to infinity. And we're going to end up with an infinite dimensional vector as k goes to infinity, where each individual prior component is going to tend to 0. And for most of the times that you're using a Dirichlet process, it's conceptually fine to sort of think of it like this, as a really, really big Dirichlet distribution, where as you're increasing the number of components, you're decreasing those individual probabilities. Right? And we need to decrease it because if we kept them constant, they'd go to the total mass would go to infinity. Oh, I was a few more divisions there. Okay. So I can take my Dirichlet distribution and I can expand it, expand it, expand it, expand it, all the way to being an infinite dimensional vector. And then I can combine that with some mechanism for generating the parameter values. This is exactly what we did in the k-dimensional mixture model. We picked a mean and a covariance from some distribution and associated that with each component. We're going to combine that here. So first we're going to sample our probability vector, and then we're going to pick some distribution over our parameters, and we're going to sample our component parameters from that distribution. Right? So the Dirichlet process is this combination of an infinite dimensional Dirichlet and a mechanism for picking parameters for each component. Right? So we specify it in terms of these 2 parameters, alpha, which is that value that we used in our original Dirichlet, and h, which is some distribution over our parameter space. Now, 2 things that we're going to see from this, or one thing that we're going to see from this, is that we end up with a probability distribution on this space of the space theta, which is whatever our distribution h is on, and it's going to be discrete. Right? We have infinitely many atoms of probability, so we end up with a discrete probability distribution. And we write this as G, which is our discrete probability distribution, is sampled from a Dirichlet process with parameters alpha and h. So h here was determining the locations of these parameters. Now that might look a little weird because our sample here in black does not look anything like our continuous distribution h, but it's basically governing where each of them is individually sampled from, right? So this means not that it's going to look like that Gaussian, but that it's going to tend to have more atoms where the Gaussian has more mass. And then that concentration parameter alpha, that gives us the distribution over atom sizes. So remember in our basic Dirichlet, the larger alpha was, the more similar the components were, right? We were going to get closer to equal probabilities. So if we go back to our splitting, this means the larger alpha is, the less difference there is between each side of the split at each side. So this means we're going to end up like we have here on the right, with something that has a much more balanced number of a balanced set of atom sizes. As alpha shrinks, those splits are going to become much more divergent, right? So we're much more likely to have the situation where we have a huge amount of mass on one component and much, much smaller mass on the other components. And then once we've got this, it can behave in exactly the same way as we used our Dirichlet distribution, right? So just like we assumed before that we had a probability vector sampled from a Dirichlet and a set of component probabilities, now we're going to sample that infinite dimensional vector and that infinite dimensional set of probability vectors. And then for each observation, we're going to do exactly what we did before. We're going to sample a cluster indicator given by the sizes of the atoms. Then we're going to look where that atom is to get our mean and covariance. And then we're going to sample from that Gaussian. I'm assuming here that we're working with Gaussians. Obviously, this extends to other forms of distributions. So this still seems like it's going to be a mess, right? I've given you a way of coming up with something infinite dimensional, and then I've told you you should just sample from that. And that's not going to work, right? Because as we've described before, we only have infinite resources. But the reason we spent so long on properties of the Dirichlet distribution is because we can use some of those properties to help us both understand what's going on here and represent it in a finite dimensional manner. Okay, so remember at the end, just before the break, we talked about the agglomeration property. So if I have a big Dirichlet, I can sum together elements and get a smaller Dirichlet. So let's say I have my Dirichlet process, my infinite dimensional Dirichlet on, let's say, the line. I can partition that line into k components and sum up the masses in each. So this is what I've done here. I've got my Dirichlet process on top, infinitely many atoms. And then in the line below, I've picked a random partition and I've just summed up the mass in each partition. And then below again, I picked a different partition and I've summed up the mass in that partitions. And in each cases, these like blobby blue masses are samples from a finite dimensional Dirichlet distribution where the parameters are alpha times the mass of that original partition. So how does this help us? Well, remember we saw that if we had a Dirichlet distribution and then we see observations sampled from a multinomial, then our posterior distribution is also going to be a Dirichlet distribution. And this is true for each of these blobby distributions, for each of these agglomerated combined Dirichlet distributions. So if I sample an atom, can you see my cursor here?
No, we cannot see your cursor.
Oh, okay. Yes, but it's a very small cursor. Maybe I'll just like move it a lot. So if I sampled a value of x here, then in my finite dimensional Dirichlet, that would be the same as sampling an observation in this block in this partition and this block in this partition, right? And then the posterior for this middle partition for this block will then be my original parameter for that block plus 1. Similarly, my posterior for this partition at the bottom will be my original parameters for that plus 1. And this is going to be true for any possible way I can partition it, right? So this, I've messed up how I'm talking the slide. So this both gives us an alternative way of thinking about the Dirichlet process. It is the distribution that gives us Dirichlet marginals for every partition. But also more importantly, it allows us to consider what the posterior distribution is. So wherever I sample an observation, I know that the posterior in that partition is going to be +1. The only way that this can work is if my posterior distribution is also a Dirichlet process, right? So every partition I know gives me a Dirichlet. If I add one observation to each of those partitions, the posterior must also again be a Dirichlet. Because the partition is a Dirichlet, going back to the infinite dimensional space, the posterior must also be a Dirichlet process. And in fact, as a consequence of this, if I have a Dirichlet process prior and I see one observation, my posterior is also going to be a Dirichlet process where I have added 1 to that concentration parameter, and I've added a point mass where I saw that observation to my base measure h. Okay, so we've just seen 2 sort of infinite dimensional ways of thinking about the Dirichlet distribution. But let's see if we can make that into a more interpretable finite dimensional representation. So remember for the Dirichlet, we saw that we could, instead of working with pi, we could integrate that out and work with an urn scheme, right? And we could think about what do samples look like as we draw balls out of an urn. And we can do something similar for the Dirichlet process, right? So I can take my posterior distribution over the Dirichlet process. I'm actually going to skip this and move just straight to the picture part in the interest of math. We can describe, sorry, in the interest of time because of the amount of time that I spent offline due to my internet problems. I can think of samples from this Dirichlet process using a variant of the urn scheme that we saw before. So here, instead of starting with k balls, I'm going to start with one giant ball of size alpha. I'm going to put that in my urn. I'm then going to pick a ball with probability proportional to its size. There's only one ball in there, so I'm picking that one. I'm then going to check whether it's the black ball. If it's the black ball, I'm going to sample a new color from my distribution over colors. And I'm going to return that black ball plus a unit size ball of the same color, of the new color, to the urn. I'm then going to repeat. So now I'm going to pick a ball with probability proportional to its size. And let's say this time I picked that burgundy one. Now I'm just going to return that ball plus a second ball of the same color. And I'm going to do this again. So now I've got the one black and the 2 burgundy balls. Let's say I pick the black one again. I'm now going to sample a new color from my distribution over colors. And I'm going to return that black ball and the new color to the urn. And I can keep doing this. So sampling a color, returning it, or sampling the black ball and returning a new color. And this is going to build up a distribution over colors where I always have some probability of picking a new color. Right, so no matter how many balls are in this urn, there's always some probability as I'm going to reach in and take out that black ball. Okay, so let's move on to a poll question on this. And the question is going to be, what's going to happen if I increase the size of that black ball? Right, am I going to get more or fewer unique colors in n samples? So think about what needs to happen here for us to introduce a new color, right? We have a new color every time we pick the black ball out. Okay, so far we're unanimous. So if you're not sure, that's a good indication that going with your gut is likely to be the right answer. Okay. I have a question on this slide, which I'll come to after we've discussed this. So here we've said, the poll so far, we have a 100% set of people saying, if we increase the size of the black ball, we're going to increase the expected number of colors. Which, yes, this is true. We add a color every time we pick the black ball. The larger that ball is, the more likely we are to pick it. So the larger that ball is, the more likely we are to add a new color. And this fits with what we saw before, that the larger the alpha was, the more sizable probabilities we would have. And we saw that if alpha was really small, we would tend to end up with just one cluster dominating and maybe a few small ones. So if alpha is really small relative to 1, once we've picked that first other color out, we're much more likely to see that again. So someone's asked in the questions and said, we still implicitly define the expected number of clusters through alpha in the Dirichlet process. Do we really win something? And that's a great question. So yes, we are, basically we are implicitly putting a distribution over the number of components that we have. So on the one hand, yes, that's more flexible than being dogmatic, right? So we are basically being Bayesian in a sense about the number of components. Now, a good question you could ask here is, well, there are other ways of doing that. I could put a Poisson distribution over the number of components. Would that give the same thing? Right, so I could say I'm going to put a Poisson distribution over K, and that then allows me to have as many components as I want. Now that is actually going to behave slightly differently. And sometimes that's going to be a really good modeling choice. But inherent in that idea is kind of the idea that we're going to converge to a final number of components, right? That there is a true answer for the number of components, and that is a fixed number. Kind of inherent in the Dirichlet and in all of Bayesian non-parametrics is the idea that there always might be something else around the corner, right? So even if, man, I can't count quickly enough to see how many colors there are there. Even if we've seen 10 clusters so far in the 1,000 data points we've seen so far, the Bayesian non-parametric way of thinking about things is thinking, well, there always may be something around the corner, right? You're implicitly saying, I don't think we're ever going to see all of the variation that there possibly can be. And if you know that you can't see all of the variation there possibly can be, it doesn't make sense to put an explicit prior on a finite number of clusters. Now, that's going to be not the appropriate case not appropriate for certain situations. Sometimes you know there is a finite number, you just don't know what it is. Right? In those cases, putting the Poisson distribution would be appropriate. However, in practice, we often still go for the implicit definition here because it's actually computationally easier to work with, in most cases, to work with this infinite dimensional implicit prior than it is to work with a explicit prior on the dimensionality. Okay, that was a great question though. So we are being informative about the number of priors that we expect in our alpha. And actually we expect there to be roughly alpha log n clusters in n observations based on this. So we'll talk a little later about how we can change those assumptions. Okay. A more common way of thinking about samples from a Dirichlet process, but fundamentally the same as that EARN idea, is to think about customers coming into a Chinese restaurant. So this is a metaphor that comes back to David Aldous, who was a probabilist who lived in San Francisco. And I've not spent much time in San Francisco, but I hear they have very large Chinese restaurants. And these Chinese restaurants often have mirrored walls. So you walk in and think, wow, I'm in an infinitely large Chinese restaurant. And you're in this infinitely large Chinese restaurant and you need to decide where to sit. So imagine we're in this scenario, Chinese restaurant, infinitely many tables. And the first customer is going to come in and they're going to sit at the first table. Okay? Without any loss of generality, we're calling it the first table because the first customer sat at it. The second customer is going to come in and they're going to choose where to sit based on how many people are sat at each table. So he's going to choose the table with the first customer with probability proportional to the number of customers at that table, in this case 1, or he's going to pick a new table with probability proportional to alpha. And then more customers are going to join, right? So the third customer comes, he's going to sit at that first table with probability proportional to 2 and a new table with probability proportional to alpha. Next person comes in, he sits at a new table with probability proportional to alpha, or the first table in this case with probability proportional to 3, and so on. And we can build up a system for how customers come in and sit at tables in this restaurant. And this restaurant analogy, I feel really helps us understand exactly what's going on in the Chinese restaurant process. So it allows us to see that we always have some probability of joining a new table, but it's going to decrease over time. And it also shows that we have this sort of rich gets richer behavior. People are going to tend to sit at popular tables. Right? If we've seen 1,000 people at the first table and only 50 people at any other table, we're more likely to see that first table again. And this also gets to that idea that Dmitry brought up in the questions about having a implicit prior, right? So before I sampled, I had no idea how many customers these 7 people would sit on, how many customers they would sit on, how many tables they would sit at. That would be a bit rude if they were sitting on other customers. It's a random number that is going to be upper bounded by n. And we can also show that this behaves similar to the EARN schemes that we had before, right? Just as before, it is going to be exchangeable. The order doesn't matter. So we can use a lot of our inference tricks that have been developed for the Dirichlet distribution in this setting. The nice thing about working in this Chinese restaurant process setting is even though it's non-parametric, we have an infinite number of potential tables, we only need to consider the 3 that we've got here, right? And when we're considering new people, we really only have 4 options. They sit at one of these 3 tables, or they sit at a new table. So we only need to represent 4 things. That's only a bit more than 3. We don't need to think about this infinite dimensional object, except for implicitly. Okay. Let's think about another way of thinking of the Dirichlet process, which is called the stick-breaking construction. This is a way of visualizing how we get those underlying probabilities. So we could get those underlying probabilities by that infinite division step, but that's not really very practical because we don't have infinitely many times. So here I'm going to describe a sequential algorithmic way of getting that vector of probabilities. And again, this is going to help us see what's going on in our distribution. So imagine I start with a stick of unit length. So the unit length represents probability 1. And what I'm going to do is I'm going to sample a beta random variable, and I'm going to break the stick at that point. Right? So I'm going to sample a beta 1 alpha, where alpha was my concentration parameter. And I'm going to break off that proportion and call that my first atom. I've then got the rest of the stick left. I'm going to recurse on that and do exactly the same again. I'm going to sample a beta 1 alpha random variable. I'm going to break the stick at that proportion. That gives me my second atom. I'm then going to recurse again and again and again on the bits that are left, right? So as I get an infinite series of atoms. And the beta random variable is always going to give me a number between 0 and 1, but never exactly 0 and 1. So I'll always have some remainder, right? So this process will never end. It's kind of like that analog of the shooting the arrow at the tortoise, but it's actually true in this case. Okay, so let's think about this with another poll question. So I have this alternative way of generating a infinite dimensional probability vector where I generate it sequentially. I break off the first probability, I break off the second probability, I break off the third probability. Do I need to keep going forever? Right? Do I need to generate all infinitely many in order to be able to work with it? Or can I just stop? So let's consider I want to sample 10 samples from a Dirichlet process mixture model. Right. Am I going to be okay if I just sample the first 10 sticks and then use those probabilities to sample? Or am I going to need more? Or does it depend? That is not the questions I thought it was. I'm sorry. That is the next question. So that's a spoiler of the next question. Okay. So the question that we actually have is, my apologies. Is this going to give us an increasing or a decreasing set of probabilities? And when I say strictly decreasing, by that I mean the second stick will always be smaller than the first. And when I say it tends to decrease, that means it will, on average, be smaller than the first, but might not be. So it's interesting, as we're seeing, watching the poll develop on my phone, I'm seeing a rich gets richer behavior. So people are tending for the answers with the most answers. So let's consider what we have so far, but please keep answering while I'm saying this. So far, no one said it's increasing. So good. Right? I think it's fairly clear that if we're going to keep going for infinite amount of times, we're going to start getting to teeny tiny bits of the stick as we go. Right? This is going to decrease. But the question then is it strictly decreasing or not? Right? Now, remember, the amount we break it at is a random variable. Right? It's going to be in between 0 and 1. So I could absolutely pick my first break to be at 0.01. Right? That is possible under the beta random variable. And that would mean my first atom is size 0.01. And then my second break, I could break it at 0.9. Right? In that case, my second atom is going to be almost 0.9. It's going to be 0.9 times 0.999. In that case, my second atom is going to be bigger than my first atom, right? Because of the randomness. But it's still going to give us a, on average, decreasing. Right? We aren't going to get a strict decrease because of the randomness of the breaks, but it's clear that we're going to, on average, get the big atoms first and then the smaller ones. So this is a lot more useful than our infinite dividing, because it means we can first generate the important ones, the ones that we're likely to see, and then generate the tail. And then this suggests an idea of when to stop, right? Because we haven't got infinite amounts of time to generate the whole vector. So maybe we don't need to. If we're generating these big probabilities first, maybe we can just generate a few and be done. So let's say, and here's the question that I thought I was asking, but now we're a little more prepared because we've thought about the stick breaking a little more. Let's say I want to sample 10 cluster assignments. And I'm going to do this by first generating the probabilities and then sampling my assignments based on those probabilities. If I want to sample 10 cluster assignments, will I always be okay if I've sampled 10 breaks? Will that always be sufficient? Will it never be sufficient? Or will it depend? So can we have, Rodrigo, can I have the next poll up?
Yes.
Sorry.
Maybe.
Okay, so looking at the responses so far, the majority are saying, yes, that will always be enough. So let's think about this. We know that the maximum number of clusters that we see is going to be 10, right? Because we've only got 10 points. But remember, we're not generating these necessarily in the size order. Right? So it's entirely possible that if we generated the entire infinite sequence and then we sampled the first one, it comes from component 20, right? So sort of to see that as the case, we could sample the first break at 0.01, the second break at 0.01, the third break at 0.01, very unlikely, but it could happen. And then the 11th break at 0.99, right? Then the most popular cluster is going to be that 11th cluster. So while we are going to only have at most 10 clusters, they're not necessarily going to correspond to the first 10 components, which sounds disappointing. Maybe we still need to do the infinite sequence. But in practice, it's not going to be that big a deal. So on average, we've got the bigger components first. So we can start off by generating the first few components and then adding more on the fly if we need them. So let's say we have the first 3 components and they have probabilities 0.1, 0.1, 0.1. We know with probability 0.7, we're in one of the tails that we haven't got yet, right? So if we sample a uniform random variable and end up in the 0.7 probability, then we know we need to add some more components. And we can actually do this in a really nice algorithmic way that kind of tells us when to stop. So instead of sampling my probability vector, I can treat this as a sequential decision. So I know the probability of the first cluster is that first break size bk. So I sample that, and that gives me the probability of being the first one. Let's say I want to sample. I can then flip a coin with that probability. That tells me if I'm in the first cluster or not. If no, I move on to the second. The probability of being in the second cluster, given I'm not in the first cluster, is then B2. It's not the size of the stick, it's the size of the break that I made after that, right? Because I've already turned down the first stick. So I can flip a coin with probability B2. And that's then going to be the probability of being in the second cluster. And I can keep going down the line until I get a yes. And I know that could take arbitrarily long, but because we've got this size ordered behavior, it's probably not going to take that long. So it gives us a nice sort of algorithmic stopping rule for how much we need to generate. And I know that that's going to be a finite number. Okay, so we've spent a lot of time today talking about different representations, both for the Dirichlet distribution and the Dirichlet process. And you might be thinking, well, couldn't you just have given us one at the beginning and then we could move on to stuff? And I could have done. And maybe going forwards, if you use this again, you're going to pick your favorite and run with it. But the reason why I went with so many different ways of having the infinite Dirichlet distribution, of having the urn scheme, the restaurant scheme, the stick breaking, is because each of these help us understand what's going on in a slightly different way, right? It was really easy to see that rich gets richer behavior in the Chinese restaurant process. And it's really easy to kind of picture how the probabilities look in the stick breaking process. If you get into this, these also suggest different ways of doing inference. Like I said, I'm not going to super get into the inference now, though I will discuss on Friday a little bit about inference tools. But I feel more importantly, it teaches you ways of modifying them. So this then gets back to Dimitri's question about the implicit assumptions that we've made. We've come up with a model that has an implicit distribution over the number of components, and that we can describe in a number of ways. Each of these ways suggest a method for modifying our distribution. So we had our Chinese restaurant process. And we picked tables proportional to how many people were sat at that table. What if instead we decided that customers could leave after a certain amount of time? That would make us less likely to sit at that table. So now we'll have something that evolves over time, right? Rich tables get richer, but also old tables get forgotten. And that's a valid modification. This is something known as the distance-dependent Chinese restaurant process. And you can use that to do time-dependent clustering. And once you know these representations, that's a natural thing to ask once you're starting thinking about restaurants. Or what if we took the stick breaking procedure and said, instead of having the same beta distribution for each break, we have that distribution depend on how many sticks we've seen so far. And again, that's a thing that people do. So if instead of breaking at a beta 1 alpha, we instead increase that second parameter as we go through the stick breaking procedure, we're going to change the sizes of our breaks, right? The size that we're breaking off is going to decrease each time. And that's going to give us more low occupancy clusters. And that's something known as the pit-manure process. And it actually is a really good match for a lot of things that we see in data where we have a lot of low probability things. So it's a really good match for language where we tend to follow a zip distribution. So we'll talk about some of these modifications and some applications on Friday, now that we've understood the basic fundamentals of what's going on. I think I'm really rushing up against time. I just saw Sushi join the call, so I imagine she wants to tell you about causal inference. But
we're actually very well on time, so it's good that you can wrap up here, SINEAD, and we can continue.
This was exactly where I planned on wrapping up. I'd hoped there'd be questions, but I hadn't banked on the internet dying.
Yes, we will continue anyway on Friday with the next part and also the Q&A. So yes, it's a very good moment to finish.
Yeah, and I'm just going to type in the chat here my email address so that if anyone has any questions they want me to go over at the beginning of next time on this material, then I can edit that in.
Perfect.
But I will stop screen sharing so that Sushi can set up.